Hello everyone. So it's finally week 4 and we'll be done after this week. However, we do have an extra session. It's mostly tomorrow. I'm not sure of the timing yet, but NPTEL people will announce to you that when it is being held, if the timing is not yet announced. So for me, it shows where it goes. Here. So for me, it's 11. So let's see what they announce on the portal. Okay. Uh, yeah, so with it, let's begin for today. I'm Jagriti. I'm a PhD student at IIT Gandhinagar, and we have been doing this course that's by sorry, by Professor Debtut Sheet from IIT Kharagpur, which is about medical imaging and it's like basics of medical imaging, algorithmic level of medical imaging. So we started off from medical modalities, then we went into few basic image processing based algorithms, and then later last week we saw about segmentation and classification, and this week is all about the applications for it. So there is nothing as to a teaching part to it, but I just had few slides made from how I did last time. So this one's like will pretty much give you a brief overview that what this like the last week's lecture was all about, because I saw the lecture slides were like 97 to 100, but I don't think so that you need to remember concepts out from it. It's just that these are some applications that you should know and you should be aware when you are rightly working into the field there. Uh, I'll just pull up the assignment first. Then I have few other questions also with me, which can help you strengthen your conceptual based questions. If you have any further questions, then of course you can unmute yourself whenever you want and can speak up. Okay, let me just download them. I'll add my device and then we can begin. Yes, so as rightly said, so it was first about retinal vessel segmentation, and he showed us about different standard databases which are there for it. It's very essential so that it's like you are being able to specify and see how different vessels are being going there, because like there's sometimes like I myself had a case that my retinal layer had lacks and some layers and latches over there, some patches there which were left open, because of which, if at times I'll cry, or let's say I have migraine, or let's say some tension or pressure, due to which the intraocular pressure within the eye builds up, which might sometimes in case cause stroke, or might lead to some severe disorders. So because of that, this pressure inside your eye increases, and you have this vitreous humor at the backside of your eye. Now, this vitreous humor, what it does is it will the fluid, if if it has much more pressure inside it, it will start on pushing beside this retinal layer which you have, and back to it you have a choroidal layer. On a similar patch of it, you have this optic nerve connected, and that optic nerve goes to your brain for information processing. So here, what you're seeing is this dark one. This is a fundus image, or similar images like this also appear in autofluorescence based fluorescence images, or in CT, optical CT based images also. So this one is the retina, the blind spot that you're seeing, which lies in your retina. So this is like a 3D cross section of it. So that's why you're looking at that way. And these are like the vessels which are emerging out from it. So some cases, if the fluid goes in and rushes towards your layer, so you might got you might have a chance of vision loss that might hamper your day of living. And also in these cases, if this problems like this if are not counted earlier or not detected earlier, then cases like this increases. There are also cases as cataract. So surgeries are feasible if you do at very, if you are getting detected at very earlier stages, but they aren't feasible for like old age people or people who cross like 60 or 70, because after that point all the functions, how young people, or how the young architecture, the young vasculature can recover itself. We cannot say the same thing for the people who are like have now crossed a certain age, because for them everything is slower. Blood passing through there, each and every artery and vein is also very slower now. Their heart is beating very slowly with respect to the young blood. It's no longer 72 or 74 beats per minute. So that's how cases like this happen, and that's how people also say. So this is like one of the emerging problems nowadays, and with the help of image processing, now people are able to do so. So this one such modality is like, if you go to like routine eye checkup, so they'll do this fundus imaging, optical OCT based imaging. They'll check for your number of the eye. So hence, like again, if you have diabetes also, because of diabetes, at times the tension, the intraocular pressure increases, which sometimes leads to glaucoma. And these all are nothing but indeed related to your age related. So the primary goal in this case is early screening and if the pathology is being detected. So these were like from this diabetic the case and this CFO a data set from which the prof has recovered them, and some history behind it, like so it everything, how a person sees, how a ophthalmologist sees it, it's very subjective to the experience of the ophthalmologist. So one might tell you that okay, you need a surgery, whereas other might say that it's not being needed. So in this cases, it's very essential. Now, how we did in this case was, we had different patches, or we had different filters you can consider as of different frequency orders. Okay. And out of these frequency orders, we differentiated them like in between three colors, which will nothing but, if visibly you're looking at it, it will provide you a hue so that you can differentiate out from there. And then later we are making a model of pixel intensities using like something as an illumination base. So it is varying with respect to position and place and the time at which you're recording it. So for red, for this, sorry, a binary model for it with respect to time of each and every pixel for its own position and the area it is being accumulating at that place. Okay, so then you estimate its density, nothing but take a probability density function for it, add in and see the probability for it. So how the model, so in this case, everything that we are looking till now is just part of classical ML. We haven't yet touched for deep learning. Deep learning needs much more databases, and again there is a problem that if you do have a sample, let's say if you're imaging one patient, okay, for that one patient you have, let's say, five images. Those five images aren't independent images, those are like of the same patient. So those are dependent on the patient's condition, the causes that the patient might figure out. So in this case, when you're trying to train your own model, this model will have certain sample variability, and that variability is just because you're considering that one patient's data to be as an independent data set. So hence what they do is, like, towards the end we merge all of them, like we average all of them, and we ask a model to see which feature out of the ones that we have trained till now, the variability or expected mean for the models is highest or lesser. That way we select the feature which is mostly important for our models to do the classification or the segmentation, and then later we select it, and from there on we that becomes our threshold for the classifying mechanism further. Okay. So that's how it is. Like, you have a source domain. From the source domain, you pick out some pixels. Again, in this case, everything is conditional probability. So you're totally dependent on the causal conditions. You're not even looking at how the past, how the future inputs will change your model input. So it's everything based on your past input. So it's nothing but conditional probability only from your source. Okay. Now, in this case, we like previously we did look at random forest, and we saw that how many trees and then ensemble of the trees, how one merges to another, and from there, what should be the depth of a tree, how many features should you get from it, till which depth should you consider so that you get minimum variability, maximum probability, and hence your interpretation and inference for it. So here in this case, there was something which was involved as stacked autoencoders. Now, what happens in in this case is, like, last time probably we saw that it also follows similar mechanism in GANs, which is nothing but generative adversarial networks. So here you have like two different, like let's say two different objects, and these objects, one is responsible for making up your data, and another one is responsible for recognizing that data. So the first one, your generator, will try and make and will try to make some false data too, so that the discriminator can discriminate it from the true data that it wanted to train it. Now, when you do so, and then when you add your binary model into it, something which involves a below downsampling and something which involves an upsampling, something similar to a U-Net or ResNet kind of model. Now, when you do those things, that makes your discrimination to a level that it will help you differentiate in between the data or the true data from the false data that your generator was trying to make in this case. Now when you stack this networks one after another so that you get a complex input, or let's say in cases, for example, if you have multiple features to your model to be inserted into, in those cases examples like this, like if you have stacked encoders, will help you in that case. Again, there's a like last time we saw that how many layers are being responsible. So it was like something to feed into the model, something which will try and like it will try to give its own feedback out there, something which will drop the input values which aren't needed based on the minimum error variability. So those are like which help you, which helps us to classify based on the trained data set that we are looking at. And then without retraining your entire data set, now our discriminator will be able to tell you that can you, now are you in the stage that you can test it further. Okay, so that's how it's being done, but keep in mind that this is not real time. And again, there is inter-observer variability, because people who do networking, people who do machine learning, deep learning, they do not have much information about the how it goes in clinics. So we also need to know how it's being there, how the inter-variability exists amongst different ophthalmologists or clinicians who are being retraining this data from ages now, and we are directly applying it to our model, because our model at cases might also produce some false positives. Hence we need to like derive all the accuracy, sensitivity, specificity, the metrics which are responsible to tell us about how our model is performing, the performance metrics. Okay, then there's a similar case for lung CT vessel segmentation. So in this case it was like the motivation was to detect the pulmonary embolisms, blockages in the arteries that can immediately be fatal. Now, when you have blockages in the artery, your lung won't no longer be able to purify your blood there. And if the blood isn't purified, it won't go to the heart and it would just keep on moving there and there. In that case, diseases like how COVID also emerged. So it wasn't exactly for embolism, but it was more of mm, how do you say, something more which can be related to sclerosis kind of diseases where there is like some plaque buildup in the cases. But in this case it is more of a blockage because your arteries get merged up or they get swine through each other, so it cannot differentiate, it cannot like allow the blood to pass through it, and hence no purification further on. So this data set is available. So there was a challenge, SB challenge, and there they gave this Vessel 12 data set. SB is like an international conference, and I remember being a part of it like 2 years back. So they do have all kind of medical imaging modalities, kind of like all different people will go and participate there. Either one's working on networks, one's working on classical physics-based learning models. Physics, not here, learning doesn't essentially mean learning, but it can be just like you're trying to solve and look how you're able to do the segmentation just with your own physics. So it does not involve any part of training or testing there. So there they told that, okay, this lung architecture is very complex, and without CT, there are like no such modalities yet available so that you can image them. Ultrasound is being emerging. So there's this, uh, I forgot the institute, but it's in Italy or somewhere. So the group is being led by Libertario Demi professor. So he's doing something on lung ultrasound. So he's also doing similar cases, like he's using models as machine learning and deep learning them to differentiate and see. And most of the times he is being using like encoders based problems. So his own entire research will revolve around lung. So if you want to, you can always go and look at his like he's also there on LinkedIn, so you can contact with him, connect with him if you are interested into it. So yeah, so the architecture that we have in our lungs is like you have vessels, you have branches of the vessels, so you have different structures there, and the structures you can make a transform for it. So in this case, they went up with an Hessian matrix, and like you have a blob, so something which essentially the alveoli is which can similar to it. Then you have a tube, so similar to your vessels, and the plate which is ground connecting to your septal branches there. So with each of the following, then the logical shape started to match with the eigenvalues, and then you have this diagonal based matrices in your the values in your matrix. So that's nothing but your Hessian matrix. You multiply it with your vectors along the spatial coordinates. You have eigenvector for it. And then here they wanted to, so this is a multi-scale vessel enhancement based problem. So there's also one such filter for it, which is like vesselness filter. So what they do is like it is based on multiple Gaussian based problem, and here it's based on exponential. But here also, if you see, it is something that square of your data mean by the standard deviation, and here also you have some. So if you look, it is also similar to Gaussian. It has second order partial derivative matrices in there, and impulse derivative function. So at each and every spatial location. So this is a kind of filter that they apply for it, and then the matrices fall into it. So in each and every cases, you need to look at the matrices, which one matrix will follow which model and how the model should look like, because these are the ones which will tell you how the what is the performance characteristic for it. Okay. So that's how the vessel segmentation for lung is like you take a 3D CT volume. You can also load the CT data into something which is called as 3D slice render, which so you all know that CT values aren't read on some like it doesn't have any such thing as X-ray or ultrasound as or MR. But in CT, everything you read is something based on Hounsfield units, and those units are everything relative to water. So now if you are even evaluating a tissue region in the abnormal cases, or let's say in tumorous regions, that will also with respect to water. And the other ones, or the normal cases were referenced to would also be with respect to the standard water. So in this case, when you load your data into the 3D renderer, what it will do is like it will give you a matrix of all the CT values across the region you select. And when you do so, you can tell it that it's not like an AI based software, but it's like a basic. If you have ever done COMSOL based simulation, or let's say ANSYS, or if you have done some, let's say 3D modeling, it's similar to that. Something and Tinkercad or AutoCAD, it's like that. So you upload the data, select the slice that you want to segment it there, as in select it there, and then from there you get your entire matrix of structures. Now you apply different transforms for it and see if you're able to differentiate it or not. So the software has multiple many modules out available there. I don't know if they are still updating it, but it's something nice to have into your skill set if you are excited about medical imaging. Yeah. Then you have this matrix-based eigenvalue computation. Based on it, you feed in the values to this your vesselness filter. Yeah. So here also, this kind of filter, they're calling it as vesselness filter. So it might also be a part of it. But the one that I was trying to tell you had a first order partial derivative so that it's easier to solve. So computational complexity reduces there. And then the matrix for it here follows as something as Die's coefficient, which is like union of the areas lying into it, then the total area and the sum of the entire areas. Okay. So I guess we did saw something as this one previously. It was a part of disjoint probability set probably. We saw something a similar metric like this in some other context previously. Yeah. Then there's something about brain MR based segmentation. So here it will involve some imaging of T1 and T2 based images. And then yeah, so that is about the model that they were looking at and how much delineation were they able to do. And here's, so how do you see? So this is like something as segmentation volumes with respect to your consensus delineation. So consider it as your sensitivity versus 1 minus specificity curve. The maximum area under the curve you'll get when the values are like 1 and this one's lower. So you have no false positives there. So it will reach up to the top. So this is the perfect consensus that they are trying to see. And the models that they almost trained and tested were like below this line. So those were like not performing. So those are like partial segmenting models like that. And then later, They're trying to say that IIT Madras team developed a N3 like NQ based CNN, and that was a state of art because that had this variability for human experts. So yeah, if you're interested, you can always go around it and look at it. Then there comes ultrasound. So for ultrasound, it is something that you know that you have a probe, and through that probe you have to image. So there's something based on observer, the observer or radiologist who's being imaging it. Now everything is dependent on that radiologist. It's not even independent there. So it's totally dependent on it. Now there's this thing called as intravascular ultrasound. So you have a catheter. In that catheter, you have a small camera and your ultrasound probe. Now you insert it, something similar to angiography and plasty, the procedures how your heart bypass surgeries happen through. So then we insert it, let's say, through your leg or through this veins or through your stomach somewhere. And then you insert this catheter inside your body. You have a guided tube following it so that you can image it. After a point, this entire tube won't go in, but only the stent inside it, which goes past through it, which has a camera and the probe inside it. Everything in here is like we are talking about some nanometer to millimeter ranges in this probe. And then when you go, it will like try and capture the entire 360-degree base cross section wherever there is a plaque buildup and howsoever. So it will, this is nothing but a single sensor, right? It's not a linear array. So what it will do is like till a point it was able to receive signal, receive signal, receive signal. But then after some point it's not able to, because everything that is there in the plaque, this particular plaque which is being built up, it will absorb all of the signal. So that's how like just looking at that single A line, the radiologists are aware that okay, I have this area. Now that's where I need to start like digging up and remove it so that the blood flow can resume from there. So that's a medical modality or the probe which goes behind this. So it's something like circular, and here they what they tried looking at as a random walk. So something similar to gradient descent. So you look at a point, descend through it, look at its probability there. Again, descend through it, take a derivative of it, look at its probability there. So this, if you want to go and have a look at the paper, it's like backscatter statistic and random walk models for tissue characterization. So here you might also have, this paper also has a couple of more things about statistical models into spectral features based analysis. Not saying that learning this is very essential for you or what, but it's something which will help you get more idea into what we are learning about. And then yes, they tried doing this multi classification based analysis, and they saw that which regions were differentiated. So everything in here, since it's a probe which we are being like guiding it through and manually moving it through your arteries and veins, it's entirely dependent on the observer or the radiologist who is doing the procedure there. Okay. Yeah. So this kind of models, like we don't have any ground truth in this cases. So previously, so this probes are now like FDA approved and they are there in clinics. So people do surgeries using it. So something similar to your endoscopes, but that thing has a camera and it works on NR, IR based, infrared based technology. So it is based on light based principle, not sound. What is being done is, so you don't have efficient models for it. So people do something as organ on chips or lab on chips based model, and further they do some ex vivo like excised tissue based specimen imaging, and further than that they do some animal imaging based models, and after that they do everything on humans. So going directly on human is totally like a big chain that you need to follow if you need your research to be translatable in that case. Yeah, so in this case, then they told that for retina, it was different. You had a fundus. For lungs, we have a CT volumetric taste analysis. Brain, whenever you consider brain, it's always MR. But nowadays, there is ultrasound, like ultrasound guided. It's like something as ultrasound guided, but you also have MR being done, so that the researchers might get information about which part of tissue cross-sectional, what depth do you have this, and till what cross section do you also have that tumor being grown there. Then you have coronary vessel based imaging. So these vessel like everything on single 1D. However, I have never seen a 2D based IVIS transducer, but I have seen a ICE based probe. So I can show you ICE probe ultrasound. So it is something as intracardiac echo cardiography. So that's how it looks like. So if you see this one, So this is something that the radiologist will have in his hand when he is doing the surgery, and this is the probe that it gets inside your body when you are being imaged. Okay. So, you see in this images, right? This B mode images. On this B mode images, whenever the probe gets inserted, in this case it is here, in this case it is here, you'll get a bright echo reflection from there, because now it is something which is made up of from, it has a metal body to it, right? So that it can transduct there inside. So that's how you can even image it and see it and get an idea about it. In cases if you do not need an image for it, so you can also get a single A line that makes your work easier and you can directly image it through. But for that, again, observer should be skilled enough or the radiologist should be skilled enough to operate kind of probe. Okay, it looks something like this. Okay. And this is your simple linear array based transducer. Okay. So there weren't much into it, and I don't even think so myself that uh, where did it go? Here? But if you have any further questions, you can let me know, or else we can start with the assignment questions.
Yeah, so since in this slide, I mean, not many segmentation techniques have been discussed, and as such, I do not have any background in biology. In fact, this is my first session I am attending.
Oh,
So, I mean, is there any standard pipeline available to pre-process the medical imaging data, or do we have a pipeline specific to a particular area, like whether it's belong to the lungs or to the eyes, and in that sense?
yes.
And to what extent the understanding of the medical or the biology field is required to progress in this area?
Yeah, so everything in here, so again, it's very specific to the organ that you're trying to image and the problem that you're trying to solve. So, as we saw for eye also, it can be related to your retina, can be related to your choroid, can be related to your lens, can be related to your the lids. So everything will have its own different pipelines, and where are you specifically looking at, the problem statement will differ, and hence your imaging pipeline will change. In this case, it was vessel segmentation, so you know that you need to apply models like this. But whenever you're working with medical data, everything is important to be related or referenced back to the standards, which is nothing but something which is going from clinician's own perspective. So let's say if I'm trying to image a tissue, and that tissue, I don't know its properties are what about, so I'll need a histopath for it, right? So if I'm imaging it, histopath essentially is like biopsy being taken, slides being stained, imaged it, and then they'll tell me that what type of cells are in it, what type of vessels are in it, if it does have a something architecture of a tumor. And then based on that morphology, I'll be able to train my model accordingly, so that when at all I'm trying to image a real tissue, a real human organ, then my model will explicitly tell me that if it's correct or not. So for each and every organ, pipelines and disease conditions, everything is dependent on it. And to make your modalities, your algorithm totally independent of the observer, the person who's trying to do this learning based analysis also, you really need to do your, like, it's not entirely dependent on stats, but it's dependent on mathematics, how you're trying to derive your model to that specifically biological conditions. You need to see that which particular variable that you're looking for, can you try to make it system independent. That way, if you're even trying to look at different systems also, let's say one from GE, Philips and all, everything will give you different system dependent output. But totally towards the end, if you want to get some trends which are independent of it, you'll also need to consider system dependent parameters there. And
Thanks.
for case of biology, like this, for this course, you don't need to worry about much into biology. This is more of only for medical imaging and then further into machine learning based algorithms. So for now, like if only you go and have a look into, like, I won't say about convolutional neural networks, but though if you just have a look into basic, let's say random forest, that's what we did in week 2 and 3. And then for medical imaging modalities, you can have a look for lecture 1. It's pretty brief into. So you have X-ray, CT, MR, and then ultrasound. PET spec weren't taught by the instructor, but that's fine. And For models, you can always yeah, there are something about spectral features. So for spectral features, you can look basic statistical based features like mean, median, mode, and there are some image processing based algorithms like which are like your conventional image processing pipelines, which people no longer use today. But these models help you gain idea how you can further integrate into this large data driven based models.
Yeah, and how does a typical data set related to this area look like? Like raw data set and which is available for the researchers to explore. How does
Yeah.
it look like?
So, in cases like medical data are all into like people do prefer DICOM based formats, and this formats will always have your matrices given to you. Okay, so that will be essentially dependent on your channel number of sensors and the depth that you're trying to image. Be it your MR data, CT data, or let's say ultrasound data or X-ray data. In terms of X-ray, it will have the information would be encoded in terms of attenuation. In terms of city, it would be something based on this Hounsfield units that we talked about. For MR, it would be echogenicities. For ultrasound, it's also echogenicities that you're looking at. So wherever you like try and see, it will be just be matrices of some pixels, intensities, and values given to you. But what those intensities and pixels are trying to tell you about, you'll have to study about the modality itself so that you can see and you can identify which feature that you're trying to look into there.
All right, thanks. And would it be possible for you to give a small demo of, I mean, the first few steps of the handling of a raw data, sometimes in your problem solving sessions, maybe next week or some other time?
Yeah, sure, we can do like I have some ultrasound based data. So if you want, I can teach you all how to look at an A line, how to make its B mode images, how to look at its probability density functions. So we can do that.
Sure. That would be really helpful if you can do that.
Okay.
Yeah. Thanks.
Okay.
Thanks, Ita.
So with that, we can start the assignment solving session then. I'll share from my tab. Okay. So since this week wasn't much into theory and it was just application solving, so I have some theory-based questions also. So after this week for assignment, if anyone's interested, we can solve those also. Okay, so first question, there are some kappa scores which are used to indicate what. So these kappa scores lie for like retinal vessel-based segmentation there. And whenever vessel segmentation, so in this case, it will tell you about the inter-observer-based variability. Okay. Then here, big data deluge in whole slide imaging can be resolved by using what for training the big ML algorithms. So that is something based on your solving based problem. So what do you think? What can you do here? So do you just select the center part of the slide that you're imaging, or the whole slide, or will you select random extracted slide patches, sequentially extracted slide patches? So it is similar to how we studied about random forest based ensemble based imaging, where we are trying to average it out so that your error will decrease and your inference based values will increase.
C seems more viable from the
Hmm.
ML viewpoint, that I randomly extracted the patches and then I can do some kind of averaging or some kind of.
Application. Yes, exactly. So this one will help you reduce the observer-based variability also. And something if you're like, let's say you're imaging an entire slide and within that slide, if at some patches you have some higher hue or lesser being stained, so it will also reduce the noise across the slide. So will also in turn reduce the bias there also. Okay. How does multiple sclerosis lesion manifest its appearance on a T1 weighted image of MR? So we looked at why T1, how T1 and T2 were varying. So this multiple sclerosis lesion, what is sclerosis is something which will eventually eat up all the vessels. And in this case, we are looking at, let's say, eye or can be CT also. They haven't specified. Oh, sorry, it's brain. Sorry. It's brain. So when you have, oh yeah, of course, when it's MR. So when you're doing MR of brain, if you have multiple sclerosis regions, somewhere it is like you have no longer vessels being there, how it will appear in T1? Would it be bright, dark, what? So lines or spots?
Spots, yes.
Yes. And which ones? Bright, dark?
Bright.
Exactly. Okay. Myelin sheath damage. So where is this myelin sheath? So in cases of it can be in your eyes, can be in your brain also. The sheath is nothing but part of your neuron. So it will help you pass on information faster. So if it's being damaged, it can be diagnosed using what? Either using intravascular ultrasound or MRI or fundus imaging or what. So it's something based on, it is like it exists in neurons. So if you have your neuron
Oh, yeah,
and then
MRI.
exactly for your MR. So here is what you have this myelin sheath inside it, the layer which is protecting it. Okay. Which circulatory system is responsible for spreading of breast cancer? So your blood, nervous system, lymphatic circulatory system. Which one?
Lymphatic circulatory system.
Mm. Whereas in breast, you have multiple lymph nodes being connected. So the blood supply is not by through them, but it's through the lymph node. So because of that, if you at one place, if you do have cancer being developed, it will cause metastasis and your entire lymphatic circulatory system would get affected due to it. Okay. Which condition is screened using IVIS imaging? We looked at an example for it just now.
Plaque formation.
Yes. Then this is something about Hessian matrix that is used in this Wessel filter being imaged. So here they are asking that if H is the matrix operator used in this, measure the HF, the magnitude for it in terms of the values being given as. So we didn't look at it, but it's the last
C.
vector. Exactly. Square root of the vector square. Okay. Now, this is something which is like extra information. If you just Google it out, you'll get an idea about it. How many loss layers does a Google net have? But this net, I don't expect you to know all the models and networks there. Neither does the instructor does. But it can have either of them. But usually the number of loss layers are like 3. Okay. Uh, then. What is this? Something about evaluation metrics for abnormal tissue segmentation in an image. So what does that LFPR stand for? So you can easily stand rule out this one. What is PR? It is for abnormal tissue segmentation. You no longer need to remember for what it would be about. Like if you even see the abnormal tissue.
Predictive rate.
Sorry.
Predictive rate.
So it's a positive rate
Positive rate.
for a lesion. So it's a false positive rate and for a lesion, because it's an image that we're looking at and not in terms of pixels or model based analysis. If it was a model, it would be predictive, but it won't be this Lagrange. It's learned. Yeah. Which of the following metrics are not asymmetric? So that was something in CT and brain also. So this is more of an direct question. Either it's PPV, DICE, or average Hanstroff distance, longitudinal correlation, LTPR. Like honestly, I don't even know the full forms for it. But DICE was one of the ones that we saw, and other ones are not symmetric. Are not asymmetric. So which are symmetric? Distance cannot be. Rates cannot be. Dice coefficient was because of Gaussian being involved there. And then I don't know which other PPV. I guess we can search it out. And that says B. So dice and then this longitudinal correlation. Or else like tomorrow's session, I'll check it out and tell you guys about it. Okay. Sequentially extracted slide patches do not serve as a solution to which problem in whole slide imaging? So do you have loss there, classification, segmentation, or big data deluge? So you know what this means, right? So if you have sequentially extracted patches, it won't serve solution. So it will does serve a solution to your whole slide classification, whole slide segmentation. So those are like essentially removed from here. Then you have image information loss, which cannot be the case because you're sequentially imaging the whole slide till you imaging the whole patches of the slide till you image the whole slide there. So this is also not the case. There are problems with big data deluge because here when you have multiple like overwhelmed data and there are different variety of the data, when you're trying to analyze it, it would then be confused, or like you'll have your model be trained on a fixed set. So then later if it has some different variability in it, or some slide goes to another, some patch is being fed to the corner or top or center, then it won't be able to classify or segment. So it will thus pose a problem for whole slide imaging when you're doing this big data deluge based cases. Okay. What does an autoencoder consist of?
Both encoder and decoder.
Both. Yeah.
Yes. 13th. Yeah. So this is about segmentation. We have a ground truth for segmentation for image I, which represents I was image I, and R represent the result of segmentation by an algorithm. Then the true positive rate is being given by what? So here, bear in mind, this is like complementary. So the areas which do not involve are there. Okay.
I'm not sure. Would it be C because G intersection R will give something common, and then this complement will give something which is there in G and which is not there in R. The G complement intersection R means G minus R, set theoretic minus.
Yes.
So I'm not sure. It could be C.
So in G, if you have no area belonging to G and it's intersecting with R, here it's being told that G is the ground truth for segmentation of an image I, and R is the result for the segmentation. So essentially, you need to compare it with G, not with R. Right. So this is, you're right that you have figured this one and this one, but there are cases which one should be complemented here first. So this is the ground truth. So from ground truth, you should subtract the result that you are getting there. So this one.
Yes.
Okay. That's A. And then there's this kappa score, which indicate no agreement among the different observers when its values are like. So we didn't look at this ranges for it. It does tell you about the inter-observer variability. So simple, if it does have a zero value, it will show that there's no agreement across different observers. Nothing as such. So a range are like from -1 to 1. If it's zero, no agreement. Then there's about longitudinal multiple sclerosis lesion segmentation challenge. There would be no questions about this, that which dataset includes about what, but here they're asking about which type of MR scans would it have. So it will have in, I guess, all datasets probably. Yeah, it does have datasets about everything, T1, T2, proton densities, flare, everything. Can go check it out. How does the depth of a CNN with a sigmoidal activation affect the value of its gradient? So there are like three terms here. You have depth, then you have a sigmoidal activation. We looked at the function last time, and then you have something as gradient. So the options are initially gradient decreases, then increases as a depth of the CNN increases. Gradient decreases as this, gradient increases as that increases. Value of gradient has no relation with the depth of CNN.
So gradient decreases with as the depth of the CNN increases, I guess, because of some diminishing effect of gradient.
Exactly. So
Okay.
as in how you go into much more depth, your networks are being able to classify it more appropriately because now your area that you're looking at is also smaller. So your gradient will eventually decrease as in how the depth of CNN increases. So here depth is essentially the networks that you are inserting in for training and testing phases. Okay. In the context of Frangi's vesselness measure, what are the two other factors apart from intensity itself? Yeah, so we had L, B, lambda, and in the position vector itself that are considered in Taylor series expansion of intensity being represented as this one, and where x naught is the spatial coordinate and then s is the scale. So which were the others that we looked at? One was matrix based association, and one was that we just heard of the keyword now.
Hessian and
So gradient and Hessian.
Exactly. Hessian and gradient. Okay. In the context of evaluation of metrics for segmentation, what does PPV denote? Okay, finally we know the full form for it. Positive, which value? Positive
Something
prediction,
related to predictions. So maybe positive
prediction,
predictive value. Positive predictive
positive
value.
prediction value. Oh yeah, yes. Okay. What is a major challenge in tissue characterization of blood vascular system using IVIS ultrasound images? So it will only identify heterogeneous tissue composition, none else, discriminate necrosis from shadow, none else, discriminate dense fibrous tissue classification, and none else. So that's a major challenge in IBIS. Which one? And bear in mind that this is ultrasound that we're talking about. And in IBIS, it's just a line. Although they said that it is 2D, but 2D IVIS is like consider the size of the probe being inserted into your body. So mostly in clinics, what they do consider is only 1D IVIS probes, like single phase probes.
all.
All.
Okay.
Because ultrasound, like it's very difficult to differentiate a homogeneous versus heterogeneous tissue. So it can either tell you a heterogeneous tissue. If you do have some plaque buildup there, it will be able to show you some changes. It will get absorbed. The signal will get absorbed. So the reflection that you get would be bare minimal. So can only discriminate some necrosis from shadow. And then if you have, so this is like the major challenge out of them all. So if it will ask you something as like order of options in these cases, because one is fibrous and one is calcification. So calcification is stronger, which is why, because it will have some calcium based deposition there, and because of which it will appear as an hard tissue for ultrasound, because it will like essentially reflect everything. So energy you're getting more and more. But fibrous tissues do have like fibers which are like built up and like which are being like stiffened up because you don't no longer have any active blood circulation in there. So which will like eventually turn up to cancer and after which they proliferate and increase and all. So in that cases, it's like only discriminating in between dense and calcified tissues is also the major problem there. Okay, what does ultrasound signal confidence indicate? The phase, amplitude, or fidelity of the signal being received?
See fidelity of signals
Fidelity.
received.
Yes, exactly. Okay, so I guess with that we are done with these questions. I have few other questions. If you want, you can have a look at those. So, yeah, I guess this one we can do, and the other ones I can upload. So answers are directly written below it. So if you want. So fundus imaging was for which disease that we looked. So it's for like diabetic retinopathy here. And why so an explanation is also added. Then which structures must be localized and segmented in retinal image analysis. So it's a vessels that you're looking at. So this ones and the other ones are interrelated to retinal image analysis. Uh, let's say D. One of the key challenges in retinal image analysis is what?
Image compression.
Yes, I do think so, but it's the quality of the image that you're looking at. Because
Uh,
these are the vessels that you're trying to differentiate, right? So if you don't have enough resolution based images, so you won't be able to differentiate there.
Also, what did Prof said in his one of his lectures? Like he was talking about some muscles, right? Muscle textures or something.
Mm-hmm.
Was he talking about blood vessels or the eye imaging retinal scans?
Eye imaging retinal scans.
Okay. Okay.
Okay, this is like data set, it's not needed. Which data set? It's also not needed. Chase is like your retinal data set, it's also not needed. Yeah. So vessel detection in fundus images is important because it will help you report retinal based pathologies. Um, this is also not needed. So what does inter-observer based variability refers to? Variation or differences in between what?
Uh, Variation between imaging.
So that's system effects.
Oh yes.
This is inter-observer variability. So this is in differences in
Okay.
between the human annotators. Okay. I guess this one's also nice. So if you have a retinal imaging based model, which components would it include and why so? So for retina
All.
based, yes. So you have a reflection based model, it will eliminate at a point, and this point switch function will help you focus where at which depth you're trying to take an image from. Okay. Photon tissue interaction, this is fine, it's not related. Yeah, this one. Autoencoders which are used in retinal vessel segmentation are what? Which will do what?
Uh, Increase the resolutions.
Mm? Autoencoders.
Oh, okay. Oh, reduce noise.
Feature
No.
to learn feature
Learning.
representation.
Yes,
Oh
exactly.
yeah, my bad. Yeah.
So we're essentially learning in this case. Okay. This is fine. Just models. Yeah, domain adaptation aims to do what? Train on one data set, apply to another, increase, reduce, or compress.
A train on one data set over the other.
Train on one and then test on another. Data set used to train the model is called what?
Source domain.
Hmm.
Yeah.
Source domain. Let's say this is fine application based, and this is also not needed. This one. Vesselness measures in CT images are computed using what?
Haitian matrix.
Hmm. This is fine. Yeah, here. Which metric is widely used to evaluate segmentation performance? We look for retinal vessel segmentation.
Dice coefficient.
Nice.
Dice coefficient. So I guess that's it. The other ones are also similar to it, like something, I guess, extra question here. Yeah. Let's see if there's something extra into. Uh, these are like more from bio perspective, like how you do see it. There are some like learning based models. Lot of similar. So yeah, this one was nice. I like this one. So operator. So in this case, what they might do is like you will confuse it you from a Hessian matrix with respect to a Hessian operator. So matrix is something where you're looking at diagonal eigenvalues, whereas a operator, which is nothing but a multiple like order of Gaussian filters being combined together. So whenever you're looking at lung CT segmentation, and not retinal image, it's always Hessian that we're looking at, because the other ones are like frequency based, and this is the ones which we're looking at analytical domain. Okay, this is this also, and for tissue type. Yeah. So here for physics of ultrasonic based imaging, which physiological property is being probed to infer about the tissue type? So ultrasound is all about the reflection that you get back, the backscatter that you receive back, right? Because essentially you're sending one signal and then trying to receive it back through the same transducer or another transducer. So it's not at all electron, nothing about efficiency, nothing about light. So it's only about the backscatter density, how much energy that you're getting back. Okay, this is fine. Yeah, so I guess we moreover covered everything. If you have any further questions, do let me know. Or else tomorrow, according to the announcement, we'll meet tomorrow for the extra session then.
And from where can I see the recording of the previous sessions? Because I
Yeah,
did
I
not find the
guess
link on here.
I'll show you. So if you go into the lecture slides, I guess my screen is visible.
No, not yeah, visible now.
You look into extra courses and then here, wait. They had it, they removed it. I don't know what happened. Let's just see on announcement. This extra session, this is fine. Here, if you go into this one, it will have recording flip. And in here, I'll upload the lecture that we had today. And if you go into this one, that's my OneDrive folder link, where the like sessions with respect to week 1, 2, and 3, 4, and the assignments that we have solved till now, everything is added in here.
All right. And would you recommend some literature or so that I can understand this medical jargon? I mean, these terms which are I'm totally unaware of.
There are like big books for it, like, but I guess for beginning, you can just look into Princeton links. I'll add the literature sheet tomorrow if you just want to begin with for basics. And I guess I'll add it into the OneDrive folder today. You can have a look from there.
Sure. Yeah. Thank you so very much.
Thank you. Okay, then. So thank you for today. I will end up here. Thanks for attending.